single object, so a single So for a single object, let's say it's something like a block again on a surface, and there is a resultant force acting on the block. Now we know if, let's say this is the only force acting on the block, and let's say this block has got a mass m. So we know from Newton's second law that this resultant force will be equals to mass times acceleration. We know that acceleration is just the derivative of velocity with respect to time. Now we can change this around because the mass does not change with time. So we might as well write this as the derivative with respect to time of mass times velocity. Because if you take the derivative, mass is just a constant, so it just pops out in front, and you're left with the derivative of velocity versus time. And this quantity here, in brackets, we call the linear momentum. So the linear momentum we will denote by a vector p is equals to the mass of the object times its velocity. Right, so it's just, for now, a quantity that we've introduced. The only thing at this point that this allows you to do is you can write Newton's second law in a slightly tidier form. So you can think of linear momentum as that thing we must take the time derivative of to get the force. Right, so that's, right now this is not such a big deal. It's a slightly more shorter way to write Newton's second law, but at this point I will forgive you if you ask, so what? Why do we define this quantity? Well, to answer that question in part, let's think of this object in terms of this whole idea of systems and external forces that we introduced when we did energy. So in this case, our system would just be the mass m, and the external force is this resultant force acting on the object. So this is a very simple system. The mass m is our system. Anything that's not the mass m is external to the system. So something coming and pulling the mass or pushing the mass is an external agent acting on the system. Now, why do I want to split hairs like this? Because if we now look at systems containing more than one object, we get some interesting results. So let's consider a system containing more than one object. So let's just say it's got two objects. Let's call this object 1. Let's call that object 2. And we want, well, let's assume that these two objects somehow interact with one another. So they're not making contact, but we know we don't need physical contact for an interaction to exist. For example, if this is two big planets, they will attract each other due to gravity. Or if one is an electron and the other one is a proton, negative charge, positive charge, they will attract one another. So let's work in a very general case and say, well, we don't know what it is. It can be gravity, it can be an electrostatic force, but there's a force from particle 2 on particle 1. And similarly, there's a force then from particle 1 on particle 2. And just to make it more general, we can say at this instant, let's say this particle has got some velocity v1. Let's say this particle has got some velocity v2. And our system we define as just being particle or object 1 and particle or object 2. So this is our system. Anything that's not particle 1, particle 2 is not part of our system. So we said an internal force is a force from one object in our system on another object in our system. So this force from particle 2 on particle 1 is a force from one object in our system on another object in the system. So this is an internal force. Similarly, the force from 1 on particle 2 is a force from an object in our system on another object in our system. So this is also an internal force. Now there's no guarantee that this is it, so let's, just to make things more general, say, well, there's some sort of external force acting on particle 2 as well. And there might be some sort of external force acting on particle 1. So this is now pretty general. Now let's start taking this towards momentum. The first thing we can do is we can say, well, I've got two forces acting on particle 1. So the resultant force acting on particle 1 is just the sum of the forces acting on it. So it will be the external force acting on particle 1 plus this force from particle 2 on particle 1. So this is the resultant force acting on particle 1. We know this has to be equals to the mass times the acceleration of particle 1. And from our definition of linear momentum, we know this has to be equals to the time derivative of the momentum of particle 1. Remember, just momentum is equals to mass of 1 times the velocity of particle 1. Right, so that's just, so we can write the resultant force on one particle as a time derivative of its momentum. So nothing new there. Same goes for the second particle. The resultant force on it is equals to the external force acting on it plus the force from 1 on 2. And again, this is just equals to the time derivative of its momentum. Now we're going to do something slightly strange. So far when we looked at motion, we said, okay, if you want to sum forces, we always only sum forces acting on a single object. But we know we can add vectors together that don't have the same point of application, that are in different points in space, as long as it makes physical sense. So let's just see, where does this bring us if we add the resultant force on particle 2 to the resultant force on particle 1. It does not mean those resultant forces act on the same object. It's just two vectors, and we want to see what we get if we add them together. Because we can add vectors together in any way we want, but we must just make sure that we interpret that sum correctly. So when we look at free body diagrams, we know we can interpret that sum as the total force acting on a single object, which gives us a total acceleration. We don't yet know what we will get if we add different forces acting on different particles together. So let's do that and see where it gets us. So let's evaluate then the resultant force on 1 plus the resultant force on 2. We've got expressions for both of this. This is just simply the external force acting on 1 plus the force from 2 on 1 plus the external force on particle 2 plus the force from 1 on 2. We can simplify this. We know from Newton's third law that for every pair of forces, action-reaction pair, the two forces must be equal but opposite. So if particle 2 attracts particle 1 with the force F21, and particle 1 attracts particle 2 with the force F12, we know from Newton's third law that those two forces are related. So we must have that F12 is equals to negative F21. So if we put that into this expression, we find that that now becomes negative F12, and that cancels out. So what we're left with is that the sum of the resultant force on 1 plus the resultant force on 2 just gives us the sum of the external forces on the system. So in this case, this would be the external force on 1 plus the external force on 2, but both of them are external forces, both of them somehow act on the system, so I'm just going to write that. But we also know that f res 1 we can write as the time derivative of the momentum of particle 1, and the resultant force on 2 we can write as the time derivative of the momentum of particle 2. And this is now equals to the sum of the external forces. We can write this as the time derivative of the sum of the momenta, P1 plus P2. Right, so if I just differentiate, I get exactly what's there. This is now equals to the sum of the external forces. Now we can simplify this. We can say let P1 plus P2, so it's the momentum of particle 1 plus the momentum of particle 2. Let's say that is now the total momentum of the system. So we get that the time derivative of the total system momentum is equals to the sum of the external forces. And what's interesting is if the system is now isolated, so an isolated system by definition has got no external forces. So for an isolated system, we have that the sum of external forces is equals to 0. So we've got that the time derivative of the system momentum is 0, which means the system momentum itself is constant. So it means, remember when we had isolated systems, we said, okay, well, the mechanical energy of an isolated system is constant. Now we've got another quantity that's constant from an isolated system. It's called the linear momentum of the system itself. So this means if you know the momentum at one time of the total system, so you add up the momentum of all the objects in your system, you get a number or a vector, more precisely. You know at some later time, if you add up all the momentum in your system, you must get the same vector out. So that's what this equation implies. So we've now found a new quantity, the total momentum of the system, that is conserved if this is an isolated system.